Hi again, it's Liam. We're starting lecture 2, probably in the same little packet on Haiku, but this is still on charge and current, and this one is about current in different forms. So if we look at our learning outcomes for today, we have to be able to demonstrate, define and apply current as the movement of electrons in metal and ions in electrolytes. We're going to talk about that almost straight away. Conventional current and electron flow and their differences. And Kirchhoff's first law. Now, we made reference to Kirchhoff last lesson, but we're going to talk about it in detail now. But first, current in different forms. So, in a metal, current takes the form as the movement of electrons. Now, if we put some sort of, I'm going to make a reference to a word that you might not be familiar with, but that's potential difference. But basically, all I'm going to do is put a positive at one side and a negative charge at the other side, and the electrons will be attracted to the positive side and, in turn, repelled from the negative side. Now, we're going to keep that in mind, and we're going to explain that in a much later lecture about what drives this process, but for now, that's all I have to know. But this happens as the electrons generally are allowed to move inside a metal because of metallic bonding. Now, metallic bonding, as you probably know, is that they just sort of loosely share electrons, like a very weird relationship in the 60s. So, the electrons are shared between these ions, and as long as they have approximately the right number around them, it all works. So they're just allowed to move around. And they don't move in some straight path. They'll move all kinds of directions, but their net movement will be from negative toward positive. And that's how current is sustained in a metal. In an electrolyte, or a fluid with something dissolved in it that allows us to pass a current through it and it works, in an electrolyte, such as salt or sodium chloride dissolved in water, we can pass current in a different way, and that is through the movement of ions. Now, we have a negative side and a positive side to a battery or a cell or whatever it is that we're doing, and if we poke our negative side into some water, we call that a cathode. And our cathode has an alternate side, and that is called the anode. I'm sure you're familiar with this from chemistry at GCSE. But the cathode, being negatively charged, attracts cations, also known as positively charged ions. Right? They move through the fluid towards the cathode. In turn, anions, have I said that correct? Yes, I have. Negatively charged ions will move towards the anode, and in that term, current is communicated or carried through our circuit. It's carried through the fluid. Does that make sense so far? Cool. The next thing we need to be aware of is the difference between conventional current and electron flow. They're both the same process. One is just the actual thing that's taking place, and that is that the electrons are being forced to move within our wires, and they move from the negative to the positive side. We can see the path of Mr. Electron here. And conventional current is what we thought it was prior to the discovery of electrons, and that it moved from positive to negative. That's pretty easy, isn't it? Right, the next thing, on that note, you just need to remember that that's the case. We use conventional current in our equations in AS and in A2. You just need to remember that whenever we're using equations, we use correct conventional current as our right direction. The next note is this. Kirchhoff's first law. And I made reference to that in the previous video, but now we're going to make reference to it again. And that is this. Our electron, while he doesn't exactly make a journey, but walking all the way from the negative to the positive, because we know that the streets or the current or the wires are full of electrons, the whole metal is full of electrons, but the whole thing sort of shifts around in that general direction. The fact is that there can at no point be an opportunity for the electrons to be taken from our wires. We don't have wild tribal electrons killing other electrons, and we don't have them setting other ones on fire for fuel, right? Their behaviour is exactly like a fundamental particle, and that is that it cannot be destroyed. And that means that any electron or any amount of current flowing in the wire in one place must be the same entering as leaving that place. Now, that sounds a bit obvious, but not necessarily. So if we imagine, I'm just going to break this down in a second. Imagine we have here current 1. So we have one current, and let's say it splits at a junction into current 2 and current 3. Current 1 must be the sum of current 2 and current 3. Now that is because electrons passing through this way must not leave. They must stay there. It is a statement of the conservation of charge law. And that is something that we will pick up later. But Kirchhoff's first law states, in effect, that all currents entering a junction must be equal to the sum of all currents leaving a junction, where a junction is anywhere where it changes. In fact, anything can be a junction. For example, if I say this is a junction here, all the currents entering it must be equal to all the currents leaving it, which is quite obvious, isn't it? So, if we look at our learning outcomes, have we discussed current as the movement of electrons in metals and ions in electrolytes? I think so. Do we know the difference between conventional current and electron flow? We should do, they're just the opposite. Negative to positive for electron flow, and conventional current positive to negative. And Kirchhoff's first law, you should look this up and get an exacting definition of it and write that down in your notes. But Kirchhoff's first law, all currents entering a junction must equal the sum of currents leaving a junction. Remember it, it comes up in your exam, we use it all the time. Right, please attempt the questions that are below this video, and if you have any problems, post that in the discussion area. But otherwise, thank you.